Hello everybody. Today we are taking a closer look on neutral axis, aka white points, and their handling within TrueLight color spaces, which is the color management framework in all Filmlight products. We will learn how to manage creative white points for different viewing conditions and how to correctly import display referred material into a grading scene, for example to verify a rendering. The term white point has several meanings because we need to consider the white point at various stages from the scene to the final display. We can identify three types of white points. We have a scene referred white point on set, a display white point at the end of the pipeline, and a creative white point or mastering white point in the middle. Within the color management software here, TrueLight Color Spaces, we will very briefly touch the white point handling on set. We cannot go into details here. It all starts with a light source which emits energy within the visible spectrum of electromagnetic waves into a scene. In simpler words, the light source illuminates the scene. All objects reflect, transmit or absorb a different portion of the visible spectrum. The reflected light falls into the camera, which itself is sensitive to different portions of the spectrum. To perform a white balance on set, we focus on an object with a flat spectral reflectance curve. This gray or white patch reflects all parts of the visible spectrum at the same amount. Now in camera or later in the grading software, a white balance is performed so that the resulting camera RGB values are equal for the reference gray or white patch. Red equals green equals blue. There are several ways to perform a scene-referred white balance, from simple multiplication in linear camera RGB to log exposure offsets in a suitable log working color space, all the way to more sophisticated chromatic adaptation transforms, like in the color temperature operator or in base grade. Important is that after the white balance, the scene-referred values are identical for red, green and blue for the reference patch, no matter what the actual white point on set was. In our example, it was a tungsten light source with maybe 3000 Kelvin. The white point on set is essential for the white balancing operation, but once it is white balanced, we can forget about the actual white point on set. Now let's jump to the end of the pipeline and consider the display white point. First of all, we need to discuss how a display is specified in colorimetric terms. For any given display, 4 values are of interest to us here. We are not touching blacks in this video. They are sometimes called the 4 primaries of a display. For an RGB display, they are red, green, blue and white. These measurements are based on the CIE XYZ 1931 or other standards like Jod-Foss modified CIE or 2010 LMS. However, this should not confuse us here. It might sound strange at the beginning because a conventional display only has 3 light sources, red, green and blue. And yes, the information of the white is just given for convenience. It can be derived from the 3 primaries directly. The white point tells us something about the luminance of the 3 primaries. The red primary would give us the visual coordinate if we sent 100 display RGB value to the display. Full red, no green and no blue. Same would be for green primary if we sent 010 to the display. Blue follows the same way. Further, for white, it tells us what we would have measured when we sent 111 or full red, full green and full blue to the monitor. In the same way, different display standards have different coordinates for red, green and blue. They can have a different coordinate for white as well. So display RGB 100, which is red, means something different depending on the display standard and will look different. The same is true for white. Display RGB 111, white in quotes, can look different depending on the display standard. The 4 primaries do not specify one particular point, but an axis which is associated with the same color chromaticity but with varying luminance. We arrive at the red axis for every display RGB values of red of something, green 0 and blue 0. They all fall onto this line. Same for green. For code values red 0, green something else in 0 and blue 0, we are on this line. The same is true for the axis that connects the peak luminance and the minimum luminance. We call this the neutral axis. For display RGB values where red equals green equals blue, we are on the neutral axis. So 0.2, 0.2, 0.2, or 0.55, 0.55, 0.55. For those, we are on the neutral axis of this particular color space. As you might see here, there are many different white points and neutral axes for different types of displays. Here I have plotted the most common ones together with the thermal locus. Also, I made some color patches with the correct hue, assuming you watch this video on an sRGB display with a D65 neutral axis. In cinema, most common is the D60 white point or neutral axis. The coordinates for this axis is CIE small x small y with 032168 and 033767. Most television standards demand a technical display white point of 0.3127 and 0.329 called D65. Then the SMPTE 431-1 standard specifies a neutral axis for verifying a correctly calibrated DCI projector. We simply call it DCI white, which by the way is a terrible name for it, as we will find out just in a second. The neutral axis is very green and has the coordinates 0.314, 0.351. Because of a misunderstanding in our industry, some users assume that this white point is the mandatory creative white point for digital cinema, which is not the case luckily. The real DCI encoding neutral axis for digital cinema packages is yet another coordinate called CIEE, E for equal energy, and falls on X0333, Y0333. This white point is just a technical white point for the DCP. This one should be called DCI white, but the industry has moved on to call the greenish white point DCI white. To manage all of those various white points, we need a third white point in our pipeline, which is the mastering white point, or creative white point, or sometimes also called the visual white point. For now on, I call it the mastering white point because this is the term in TrueLight color spaces. The mastering white point connects the scene-referred neutral axis and the display-referred neutral axis. With this setting, we give the scene-referred neutral axis a visual meaning. Okay, imagine you want to create a black and white image. Black and white images are ideal for visualizing what happens to the neutral axis because we reduce the color volume to those colors only. The question might arise, what is the neutral axis of the grading stack in a scene-referred workflow? In scene-referred, the neutral axis just means that red, green and blue are equal. It does not yet have an obvious meaning on the display. Now the mastering white point is exactly that concept that specifies what scene-referred red equals green equals blue means visually. In this example, I have set the mastering color space to DCI 2.6 gamma P3 D65. And I have set the mastering white point to be the same as for the mastering color space. So that means we have defined a D65 mastering white point. Now TrueLight Color Space understands that we are viewing the image in sRGB, which also has a D65 white point. The mastering white point and the display white point are the same. So the system does not interfere with the white point as we can see in the RGB parade. Every pixel has equal red, green, blue values. The white point journey in summary looks like this. The scene-referred white point inherits its value from the mastering white point, so both are D65. The display white point is D65 too, so it is a trivial white point journey. Everything is D65. Now let's change the mastering white point to something different. In this example, I only changed the mastering color space to DCI 2.6 gamma P3 D60 and therefore define a mastering white point of D60. This change overrides the scene-referred white point and sets it to D60. Baselight now performs a chromatic adaptation transform, short CAT or CAT, to make the neutral axis appear D60 on a D65 calibrated display. We can examine this on the RGB parade on the right. Here we now see that the reds are higher than the greens and the greens are higher than the blues. It is the needed white point shift to make the image appear appear D60 on a D65 monitor. If you would measure now the gray patch on your display, you should get the chromaticities for D60. Here we can see the real color space journey in Baselight. Below the viewing color space, we see the mastering color space and mastering white point. In summary, we can say that TrueLight Color Spaces changes the RGB values of the neutral axis for each display color space so that the visual white point stays constant. In TV, frequently the mastering white point and the display white point are the same, so we have a trivial case usually. That said, even for television projects, it is not mandatory to use a D65 mastering white point. Many artistic looks can only be achieved by using a different mastering white point. However, let's have a look at digital cinema, where the display white point is always different from the mastering white point. That means for digital cinema, managing the white point is mandatory. You need to specify a mastering color space and mastering white point if you want to export a DCDM or DCP. Otherwise, TrueLight won't know what white point was used for grading, resulting in incorrect XYZ renders. To recap, the DCDM specifies a display white point of CIE at 52.37 nits. We therefore need to always correctly transform the neutral axis into DCI 2.6 gamma XYZ. Below I have calculated a few white patches for you. If we decide to choose for creative reasons D60 as our mastering white point, the maximum value of our mastering space, which is 111 in that space, gets mapped onto 0.949, 0.967, 0.970, which is the exact coordinate for D60 at 48 nits in DCI XYZ. If we want a D65 white point for cinema, then the peak of the mastering color space, again 111, lands on 0.948, 0.967, 0.999 in DCI XYZ, which again is the exact code value for D65 48 nits. If we choose the greenish white point, it lands on 0.926, 0.967, 0.949, which is again the correct value for this particular white point. At this point, I want to highlight again that this white point is not mandatory for digital cinema. In contrast, if we read the SMPTE 431-1 specification more carefully, there is even an explanation that the DCI XYZ system is designed in a way that supports many mastering white points. Last but not least, if we would choose a CIE white point, we see that 111 comes out as 0.967, 0.967, 0.967. In this example, all three values stay equal to each other because the mastering white point and the display white point are the same. However, please note that this example is there only for showing the numerical concepts. The CIE white point is very unsuitable for color grading. We can also see that in all four examples, the second value is 0.967. It is not a surprise because in DCI XYZ, the second value is a gamma encoded luminance and 0.967 is the value for 48 nits. So which white point or neutral axis should you use? It's a creative choice. The colorist should have freedom over the mastering white point, and you might want to determine it during look development. As a starting point, we recommend you to use a D60 for all symmetrical viewing conditions and D65 for all other viewing conditions like dim and bright surrounds. It is also the default choice for the ACES and Filmlight scene template when the mastering color space is set to automatic from DRT. However, other white points are valid too. We discourage users to use the DCI greenish white point because it renders unpleasant skin tones and produces magenta results when TrueLight remaps the content to D65 for television-based deliveries. So far so good. We have only discussed scene-referred inputs till now. What if we have a display-referred input in our timeline? How does the mastering white point affect the handling of content's neutral axis? There are two workflows TrueLight distinguishes. In the first scenario, we want to convert the display-referred material back to scene-referred, utilizing either inverse display rendering transform or boost range, which is a local inverse tone mapper. This results in a scene-referred image state in the stack. Therefore, TrueLight Color Spaces treats it the same way as if the source would be scene referred. It neglects the original white point, and we assume that red equals green equals blue is neutral. It makes sense because if you convert display referred material to a scene referred stack color space, we can assume that you want to further color grade the material. The second scenario is essential if you want to import your display referred material into the scene faithfully. The input and stack color space are both display referred. Here, TrueLight Color Spaces performs a correct chromatic adaptation to maintain the original neutral axis inherent in the media. If you set the stack color space to match the mastering color space, you get the correct chromatic adaptation on input and output so that the material looks as intended on your final display. You should use this workflow if you want to import display referred titles or if you want to verify and correctly present a display referred rendering from Baselight. Let's have a look at how this works in practice. Here we are in Baselight. I have chosen this example to discuss both the scene referred and display referred white point handling within the TrueLight Color Space system. We shot the scene with an ARRI Alexa SXT and we used the ARRI Sky panel to light the scene. We set the light source while shooting to 2800 Kelvin. We did not bother to change the white balance in the camera. We recorded raw so we can change the white balance later. That's good for this demonstration. What we can now observe is that the shot has a wrong scene referred white balance because we lit the set with 2800 Kelvin, but set the camera white balance to default 5600. Because we shot raw, we can change the raw settings and utilize the correct in-camera white balancing. Here I have chosen 2600 and a green tint of -2.154. You might ask why I didn't dial in 2800 to match the color temperature of the light source. Well, I derived those values by looking at a neutral object in the scene, specifically this gray patch below the yellow patch on the X-Rite Macbeth chart. I changed the parameters in the SDK so that the RGB values are equal to each other. You can see this quite right in the RGB parade when you enable RGB overlay. It is the concept of scene referred white balance, where we take a gray or diffuse white objects with a flat spectral response, place it into the scene and apply a specific algorithm to make these RGB values equal to each other. Using the raw parameters to do an exact job can be cumbersome and slow, and it is quite a manual process. A faster way could be using Basegrade, which does an LMS type chromatic adaptation transform in the balance section. You can specify any object you want to do a white balance on, not only neutral colors. Alternatively, you can even specify your own reference like an actor skin. Once specified, you need to click in the area on the image and it calculates the correct white balance and exposure for you. It might be a quicker way to perform a scene referred white balance. Alternatively, you could use color temperature, which uses a very similar chromatic adaptation transform. Again, I derive the values by looking on the neutral patch and make sure that red equals green equals blue. Another approach could be to do multiplication in a linear domain in a suitable working space. Here I use the color crosstalk operator because it has a handy feature. It has this linear button. If you press this button, the color crosstalk, which is also color space aware, converts from the stack color space to a linear version of the same color space, here from Loxy white gamut to linear white gamut. After that, in linear white gamut, I use red, green, blue scale to perform multiplications on the three components, until again the neutral patch has equal values in all the three channels. The last approach I'm showing here is widespread in scene referred grading too. Here I use film grade exposure or CDL grade offsets in a pseudo-logarithmic space. In film grade you do not need to do this manually. For this workflow we have a function in film grade called balance exposure. Now we can compare the different results of the different white balancing operations. Here is the wrong white balance, then the camera manufacturer's algorithm, then Basegrade. Visually they are very close for most colors, only extreme saturated colors come out differently. Here we have color temperature, RGB scale in linear, and the offset in log. If we look on the chromaticity diagrams, we can see there is quite a difference from the different results. You could argue which one gives the right result here, but I think it's good to have different approaches available for the color grading task. Generally speaking, I would always advise doing the bulk shift of the white point handling with the camera manufacturer supplied tools, and then do more subtle tweaks with other white point operations like base grade. If you debuy a scene shot with 2800 Kelvin with 5600 Kelvin in the camera manufacturer process assumes that the scene was lit with a 5600 Kelvin light source. The algorithm makes certain assumptions about the used light spectrum. So if there is a mismatch between the scene's white point and the camera's white point, this leads to wrong assumptions and therefore wrong optimization applied to the data. All operations downstream cannot necessarily undo those wrong optimizations. Also, the in-camera white balance might affect the demosaicing algorithms on fine details. Let's now look at the output side of the white point handling. Here I have the same shot again and made a second copy of it and reduced the saturation to 0. Baselight reduces the difference between red, green, blue to 0. That means in scene referred state, all the 3 channels have equal code values for each pixel. However, they are only identical in the final image if the mastering white point is equal to the technical white point of the display. In this case, I have an sRGB viewing color space because I assume you watch this video on an sRGB monitor. The sRGB standard defines the same 4 primaries red, green, blue and white as Rec 709 and Rec 18886. That means that the 4 primaries of my display are identical to the 4 primaries of my mastering color space. By the way, the gamma setting is not essential because we apply the mastering operations again in the linear domain. Only the description of the primaries, white point and peak luminance count here. You can see there is a match of white points because the RGB parade shows that all channels are identical. However, now if we go to the scene settings, format and color, and open the advanced tab, we can find the settings for mastering color space and mastering white point. Automatic from DRT picks a proper and suitable white point and mastering color space for you based on your viewing color space. It's typically our recommended practice. Nevertheless, we can override this and, for example, force it to be DCI P3D60. Now we can see that the red, green and blue channels are not anymore equal, but the red channel is bigger than the green channel and the green channel is bigger than the blue channel. I can override the white point settings to something even warmer like D55. And here the difference between red, green, blue increases more. However, in the scene, nothing has changed. To visualize what's going on in the scene referred stack color space, I quickly change my viewing color space to FilmLight T-Log eGamut. It is for demonstration purpose only. You should never use scene referred color spaces as viewing color spaces. You can see that the system is not applying the white point shift because by convention, neutral in scene referred just means red equals green equals blue. The mastering white point does not have any influence on your scene referred data. You can think of this setting as a tag. It identifies what the scene referred neutral axis should look like visually. Only once we convert to a display, this setting becomes relevant. Bluish D93, greenish DCI, somewhat neutral D60 and D65. Okay, now examine how we render and bring display referred material back into the scene. Before we start with the last section, I need to explain my setup here. In this last part of the video, I added a color correction to the video tutorial itself from P3D60 to sRGB, so that I can visualize both what you see within the software and what you would see on a P3D60 calibrated projector. So if I pick in the image, the RGB values tells us red equals green equals blue, but the actual video tutorial movie shows us the correct D60 white points, as we would see it on the projector. Okay, let's assume we're happy with what we see and we want to render. Let's export the 2 shots as P3D60 for reference and DCI XYZ for the DCDM. We go to Views, Render. Here I have a P3D60 reference rendering and a DCI XYZ one for the DCDM. By the way, P3D60 render is not the digital source master or short DSM. In the original definition of the DSM, the DCI referred to the graded scene referred master, either some form of log rendering or a suitable scene linear light export like ACES Linear AP0 in OpenXR according to SMPTE 2065-1. Labeling a P3D60 render as DSM might be misleading. I use ProRes 444 to show some other color relevant new features of 5.2 while we are here. In the color taking section I choose automatic. This writes the correct metadata into QuickTime files for color spaces that have corresponding QuickTime tags. I also want to take this opportunity to make you aware of another change in Baselight 5.2. For ProRes we have changed the video scaling handling. In 5.1 and before we added an additional full to legal hidden to the user. You would have needed to provide full range data for ProRes encoding in Baselight 5.1, 5.0 and 4.4 M1. To gain more transparency, we have removed the hidden full to legal scale for ProRes to match the visibility on the input side. That means now you need to provide legal range data for QuickTime ProRes and choose the option full to legal in VideoLUT. We made sure that all the deliverable sets are intact, but new deliverables need this changed VideoLUT. Additionally, you get a warning if you provide full range data. We have added another little feature to gain transparency and flexibility. The YCBCR matrix used for deliverables which encode YCBCR data. Now you can specify which matrix should be used to generate YCBCR from RGB. The automatic tagging works in most cases. We choose the 709 matrix for all color spaces but the Rec 2020 based ones. It reflects the maybe unideal but yet common industry practice. You might wonder why we have YCBCR even if we choose Apple ProRes 444. This video is maybe full with surprises, but all ProRes files Baselight generates are YCBCR. The XYZ tab uses the same settings, but just a different rendering color space. Here we have DCI 2.6 gamma X prime, Y prime, Z prime. So let's render just those two shots. I use the %L wildcard to get the strip name of the layer 0 into my file names. Now let's re-import the shots into the same timeline. Let's start with the P3D60 one. I select them and click the little blue bar to insert my selection into the timeline. What we can see here is that Baselight does recognize the color space from the NCLC tags, which also means that these QuickTimes look correct on any ColorSync managed device. On default, the material is converted back to scene referred utilizing inverse DRTs. This is not what we want in this case, so I set the stack color space for those two shots to P3D62. The working color space for these shots is display referred. It is P3D60 all the way from input to output. As expected, the render matches the timeline for both shots. Now let's repeat this with the XYZ renderings. Unfortunately, QuickTime NCLC tags do not allow to tag DCI XYZ, so we need to do this manually in this case. If I try to repeat the above and set input and stack color space to DCI XYZ, we see that the rendering does not match. In 5.2, there is a color space journey warning explaining what's going on. To view XYZ data correctly, set the stack color space to match the scene's mastering color space. This will trigger the correct white point handling on input. It should remind us to the slide I explained earlier in the video. To get the correct white point handling for display referred media, we need to set the stack color space to match the mastering color space. If set, TrueLight does the correct white point shift on input, and now the rendering matches. Again, the rule of thumb for verifying rendering or correctly view display referred media, set input to match the source and set the stack color space to match the mastering color space. If set, the media looks correct on any display. I hope this helped a bit to make the white point handling a little bit more intuitive. All the best and see you next time.